Hello, and welcome to my talk on automatic Boolean query formulation for systematic review literature search. My name is Harry Scells. This research was completed as part of my PhD at the University of Queensland in collaboration with CSIRO and the Bond Institute for Evidence-Based Healthcare. Systematic reviews are useful in many disciplines, but in this talk, the focus of our research is in the medical domain. Here, systematic reviews are used to guide clinical decisions, so for example, what action a clinician should take to treat a patient. They inform institutional practice and policy making. For example, there's a famous case of a systematic review being used to decide to ban smoking tobacco in public areas in the UK. And they also provide evidence through comprehensive literature review. Systematic reviews form the cornerstone of evidence-based medicine. So what is a systematic review? A systematic review is similar to a literature review. It's the synthesis and appraisal of all relevant documents for a particular research question. It aims to be unbiased and comprehensive, and it must adhere to strict guidelines and protocol. This ensures that the review can be reproduced. This is a high-level overview of the systematic review creation pipeline. There are many steps in this pipeline, but here it's been simplified as a funnel where a research question comes in the top, and then through a series of stages, a systematic review is produced. The reason the diagram is shaped as a funnel is because we're progressively reducing the total number of studies required to be able to produce a systematic review. But one big challenge in constructing systematic reviews is that they're extremely time-intensive and costly to produce. So the entire process can take upwards of 2 years to complete and cost more than $150,000. This is a big problem, and a lot of research is focused on reducing these costs. My research focuses on query formulation. This is the construction of a Boolean query which retrieves the literature for screening. However, most research is currently focused on automating the screening process. This is where researchers screen retrieved studies for inclusion in a systematic review. We suggest that by improving how queries are formulated will lead to less studies requiring screening and ultimately more timely and cost-effective systematic reviews. Query formulation for systematic review literature search is the focus of this talk. These queries are formulated by information specialists and are executed on large literature databases. One example of these is PubMed, one of the largest free sources of medical literature, containing approximately 30 million studies. All databases used for systematic review literature search use Boolean retrieval. Often the development of the Boolean queries is seeded by a set of relevant studies to provide to the information specialists before they begin query formulation. The protocol of a systematic review, which is a document containing the title, research question, inclusion and exclusion criteria, among other information, is also used to develop the query. Information specialists then often gauge the effectiveness of the query using these seed studies, as well as use them to identify terms to add to the query. One of the most prevalent ways of constructing Boolean queries for systematic review literature search is the conceptual approach. Here, information specialists identify key high-level concepts. These high-level concepts are then used to identify terms which relate to them. Then, each group of these related terms becomes an OR clause. And then each of these subclauses are grouped by an AND clause. But there's a couple of limitations to this approach. Firstly, this process is demanding and that it requires lengthy interactions with the search system. The approach is also far from optimal in that queries usually retrieve far more studies than required. And also, query formulation here is costly in that it can take several weeks and has significant impact on the total time and cost of a systematic review. For example, if a query retrieves excessive amounts of studies, then it's going to take a long time to screen all of those studies. So we propose a pipeline to address these limitations, which automatically constructs queries for systematic review literature search. And we attempt to do this by approximating the processes and intuitions of information specialists using this conceptual approach. We have 5 steps which encapsulates the construction, expansion, and refinement of Boolean queries. The process first starts with query logic composition. The purpose here is to derive high-level concepts of the query from a statement to form a proto-query. A statement is fed in which describes the topic of the systematic review, and the logical structure of the query is produced. We define two methods for constructing this proto-query. An NLP approach, which uses an unlexicalized English probabilistic context-free grammar parser, which segments words from systematic review statements into noun phrases, and these noun phrases are then used to construct the intermediate Boolean clauses of the proto-query. And we also have a manual approach to compare it with, where we manually segment sentences, and these segments become clauses in the proto-query. Before we move on, I'd like to draw your attention to the square brackets around NLP and manual. These are used in this presentation to signify a method in the results later, but you don't have to remember them now. Next, we perform entity extraction on each of these clauses in the proto-query. We do this by extracting UMLS entities using MetaMap from the terms in the proto-query clauses. This process models the high-level concepts an information specialist would conceptualize themselves. Note that other entity extraction methods and terminologies could be used, but we leave these for future work. The next step is entity expansion. This is an optional step which broadens the scope of the query. If it's not applied, the query may be too narrow. Our method exploits the mapped entities by mapping them into high-dimensional vector space using word embedding techniques. We then measure the distance to similar embeddings and take the top k entities with the highest similarity. Next, we take these concepts and we map them back into keywords. In the UMLS terminology, which we use to represent concepts and UMLS entities, each entity has many terms which represent it. UMLS is an umbrella ontology which is constructed by combining multiple other medical ontologies such as SNOMED, MESH, among others. We have 4 methods for performing keyword mapping, 3 of them which exploit the relationship between UMLS entities and the terms that represent them. The first is match, which just takes the original terms matched in the query logic composition step. This method can't be used with entity expansion and ignores the entity mapping step. Next is preferred. In the UMLS terminology, each concept has a preferred term associated with it. So in the example below, you can see that term C would be selected as the keyword to map in this method. Next is alias, which maps an entity into all the unique terms for an entity. In the example below, term A, term B, and term C would be mapped from the entity into keywords. Finally is the frequent method, which maps entities into the most frequently used term to represent that entity in UMLS. In the example below, the entity would map to term B as it appears twice. Finally, we have an optional post-processing step that we apply to the new complete Boolean queries. These methods seek to further broaden or refine queries. The first is stemming, which we apply by analyzing a collection of existing systematic review queries and extract stems from these queries. With the stem list, we then substitute terms in the automatically formulated query with the longest match found in the list of stems. We also apply a randomized control trial filter to the query. Filters are quasi-standard Boolean expressions that information specialists use to retrieve specific portions of a database, for example, the types of studies. To implement our pipeline and query formulation methodology, we perform our experiments on the CLAY TAR 2018 subtask 2. This gives us 72 topics with queries and titles. So we extract the title from each systematic review. We then formulate queries using different combinations of the pipeline instantiations, for example, only changing keyword mappers or applying post-processing. We then compare the effectiveness of formulated queries to simplified versions of our original queries. These simplified queries make the same assumptions as our methodology, so that we can make a fair comparison between them. This is because our pipeline does not formulate queries with some of the more advanced syntax available. This is because it's yet unclear how to integrate the advanced syntax into our query formulation pipeline. We leave this, however, to future work. First, we will explore the highlights of the most effective combination of query formulation methods. In terms of precision, we find that manual query logic composition with the matched keyword mapping method provides us with the highest precision, and the manual query logic composition with alias keyword mapping and entity expansion provides us the highest recall. And in both of these situations, we get a higher precision and a higher recall than the simplified version of the original queries. We find that between many methods, there is a trade-off between precision and recall, and these next slides discuss this trade-off and how they arise. Note that not all results are presented here for time reasons, however they are discussed in further detail in the paper. First, we look at how query logic composition affects query formulation. Here we see that there's already a trade-off between precision and recall, in that the NLP approach provides high recall but lower precision, and the manual approach provides lower recall but higher precision. And for higher precision-oriented measures, we find that the structure of the query is more important than the keywords used. Next, we compare the gains or losses the entity expansion method has over the same query without that entity expansion applied. Here we can see that there's two methods that provide a gain in both precision and recall. We find that entity expansion in general increases recall with a trade-off in precision, which makes sense because we're adding more terms into the query. And for one of our methods, we see that the expansion degrades effectiveness for both precision and recall, which we found unusual. Next, we take a look at the impact of keyword mapping. Here we're looking at the comparison between keyword mapping methods for each logical composition method. We see that for manual logic composition, there's a higher precision for all methods, and we get a higher recall for only the matched method. In terms of the NLP logic composition, we can see that we get a higher recall for each keyword mapping method, and we get a higher recall only for the matched method. In terms of the NLP logic composition, we can see that we get a higher recall for each keyword mapping method, except for manual. And these results further exemplify that the query structure is more important than the terms used. Finally, we examine the effect post-processing has on the formulated queries. The figure on this slide shows post-processing applied to the two most effective combinations of methods shown previously. We found that most post-processing results in an overall reduction in effectiveness. While sometimes post-processing can be beneficial for precision, it often goes hand in hand with a significant loss in recall. To summarize this research, we find that the methods proposed here offer a trade-off. Some methods allow for a higher recall than the simplified original queries, and some allow for higher precision, but we do see that trade-off. No one instantiation of our pipeline was able to increase both precision and recall. And we also find that the most important factor in query effectiveness is the logical structure of the query. For future work, we plan to more closely match the types of Boolean queries that are constructed for the task of systematic review literature search. Here, this means using different field restrictions and using and exploiting ontologies to further improve effectiveness. We also plan to extend the pipeline with more effective logic composition methods. This includes exploiting seed studies for relevance feedback. Thank you for your time and attention. I will now be available for questions online and afterwards via email and Twitter.